This is yttrium oxide. It's a rare earth element which has been bound with oxygen, from lasers to dental ceramics to fighter jets. And it's one of 7 rare earth elements which China this year has restricted the export of.
Most people walk past a polluted creek without thinking twice. But in parts of the United States, scientists found something inside that dirty water that changed everything.
With shovels in the ground, Ramaco opens the first new rare earth mine in the United States in over 70 years.
Beneath the orange stains and sharp smell, they discovered rare earth metals.
And here they're drilling for the first time in a decade, going deep to learn more about the rare earths and critical minerals down below.
The same metals that power electric cars, smartphones, and advanced weapons. And China, the country that controls most of the world's rare earth supply, isn't happy about it.
It's quite different from the other rare earth element mine that this is in soft rock, it's shallow, it's easy to access, and the volume of it is simply gigantic.
And we will sell it to domestic customers, and that will be our answer to China.
The shocking discovery inside U.S. rivers. If you had walked along Deckers Creek in northern West Virginia some years ago, the water would not have looked like a place anyone would fish or swim. Locals remember stretches of the creek running a harsh orange color, with rocks stained red and brown, and a sharp metal smell hanging in the air.
The purpose of this is to take the untreated mine water. The water will have a higher pH.
When the water comes right out of the mine into the creek, it's very acidic.
People called parts of it a cesspool, not a stream. Fish were gone and insects were scarce. That strange color was the first clue that something powerful was happening in the water. The problem came from abandoned coal mines up in the hills. When mining companies cut tunnels into the rock and later walked away, they left behind long walls of broken stone filled with a shiny mineral called pyrite. Pyrite is often called fool's gold because it looks like gold, but has no real value by itself. When rainwater and air hit that pyrite over time, a slow reaction starts. The mineral turns into a kind of acid. That acid then eats into the surrounding rock and drags metals out with it. The result is a rusty, acidic water called acid mine drainage that pours out of old mine entrances and seeps straight into nearby creeks and rivers. Acid mine drainage does not just make the water look ugly. It makes the stream hard or even impossible to live in. Even after mines shut down, the drainage can keep flowing for decades because water keeps moving through the old tunnels and waste piles. For years, acid mine drainage in Appalachia was treated only as a curse. It ruined drinking water, corroded pipes, and dragged down property values along creeks that should have been local pride.
The lime slurry pumps through these and goes to the chemical injection manhole where it's injected into the AMD.
It's like filling up a glass as the water, either through groundwater or direct infiltration.
When chemists and geologists started testing that same polluted water more closely, they noticed something surprising. The acid that was ripping metals out of the rock was not only pulling out iron and aluminum, it was also pulling out a group of metals most people never hear about, but that modern technology depends on. These are the rare earth elements.
What we call pyrite and water, you get sulfuric acid and iron.
A set of 17 metals that sit together on the periodic table. They show up in the magnets inside electric car motors and wind turbines, in the tiny speakers inside phones and earbuds, and in guidance systems inside smart bombs and fighter jets. In a long study of coal mine drainage across the Appalachian Basin, researchers found that this dirty water and the solids that form when it is treated can hold rare earth levels similar to some commercial ore deposits. One group of scientists working with the U.S. Geological Survey estimated that coal mine drainage outflows in this basin carry roughly on the order of 1 million to several million pounds of rare earth elements and yttrium each year, depending on how much water is moving and how strong the drainage is. They pointed out that this range could equal something like 1/10 to almost half of what the United States uses in rare earths in a typical year. The reason these strange metals gather in polluted creeks has to do with how they behave in different kinds of water. Rare earth elements tend to stay dissolved and mobile in acidic conditions. In a normal clear stream with a neutral pH, they are much more likely to stay locked up in rock or soil. In acid mine drainage, the very low pH and the high level of other dissolved metals make it easier for rare earths to peel away from the rock and move along with the flow. As that water enters treatment ponds or wetlands and the pH is raised, those metals can then settle into the mud at the bottom.
We process acid mine drainage. It's one of hundreds of plants around West Virginia where we're actually cleaning the water and we're putting it back in the river, restoring aquatic life.
Deckers Creek is a clear example of how this plays out on the ground. The creek runs for a little more than 20 miles from the hills of Preston County down into the Monongahela River in Morgantown. One of the worst sources of mine discharge sits at a site known as Richard Mine, just upstream from Morgantown. At that spot, old underground mine workings leak a steady stream of foul, low pH water into a small tributary.
It looks like a normal mountain stream. The rocks look normal, the water is nice and clear. You come down to this area below the Richard Mine, and it's a whole different story. You can see the results of the acidity and all of the high levels of iron and aluminum that enter the creek at the Richard Mine.
Before treatment, that flow carried heavy loads of iron and other metals into Deckers Creek every minute of every day. The state and federal governments, working with local groups, finally funded a large treatment plant at the site as part of a broader program to address abandoned mine problems. The plant, which came online in the mid-2020s, now keeps thousands of pounds of acidity and metals per year out of Deckers Creek and has helped trout and other sensitive species start to return. When scientists from West Virginia University's Water Research Institute visited places like Richard Mine, they looked past the color and smell and saw something else. They took samples of the sludge that forms when the treatment system adds lime to the acidic water and lets metals settle into a holding pond. In that wet orange mud, they measured how much rare earth metal was actually present. The Institute estimates that sludge from some southern West Virginia sites can hold about 1.5 pounds of rare earths in every ton of dry material. Sites in the northern part of the state can reach close to 2 pounds per ton. Those levels match or beat the grade of some hard rock rare earth mines overseas. The United States still gets almost all of its rare earth supply from China and a few other foreign producers, mostly in the form of finished goods. Having a homegrown source tied to old coal mines is a strategic advantage waiting to be developed. What makes this discovery more than a West Virginia story is that the same pattern shows up in other mining regions as well. Studies in western states, including work on acid mine drainage near Idaho Springs in Colorado, find that water draining from old hard rock mines also carries raised levels of rare earth elements, which move into solids when the water is neutralized. In other words, polluted creeks and treatment ponds across several states are quietly acting like a network of man-made ore bodies that refill themselves as long as mine water keeps flowing. To understand why that matters, it helps to look quickly at how rare earth metals are usually produced.
Normally are found in very, very low concentrations. This is probably running something in the 25% grade, which is remarkable. To anyone who has ever worked with rare earths, this is a thing of beauty.
Traditional rare earth mining often starts with huge open pits or deep underground workings that dig up rock holding only a small amount of useful metal. The ore then has to be crushed, soaked in strong chemicals, and pushed through many stages to pull out each element. Along the way, miners often have to handle radioactive elements like thorium that sit in the same rocks as rare earths. Those steps raise costs, create large waste piles, and often stir up fierce local opposition, which is one reason so much of the mining and processing ended up concentrated overseas. By contrast, river systems affected by old coal and metal mines have already done part of that work on their own. The natural chemistry in the abandoned tunnels dissolves the metals and sends them into nearby streams in liquid form. Existing treatment plants, which were built to fix water quality, already pull metals out of that water and concentrate them into sludge. For someone looking for rare earths, that means the costly early steps of digging, crushing, and first separation have already happened without extra blasting or drilling. The feed is sitting there as a wet, metal-rich mud that must be handled anyway to keep the streams clean. It is one thing to find hidden metals in river sludge. It is another to turn those findings into a steady flow of high-purity material that factories and defense suppliers can actually use. That challenge takes the story from the chemistry of rivers into the realm of full-scale engineering, where the real work of turning waste into a new resource begins. How the U.S. turns toxic sludge into valuable metals. In a treatment plant, the mine water flows into large mixing tanks. Workers add a white powder called lime, which is a common alkaline material.
All this work we've been doing with acid mine drainage over the years has had one objective, and that is to clean up watersheds, clean up creeks, all those attendant benefits.
Lime pushes the acidity down and makes the water less harsh. When that happens, a lot of dissolved metals start to turn into tiny solid particles. Those particles are heavier than water, so they begin to sink.
All of the sub-watersheds in the Deckers Creek watershed, Canes Creek was the most heavily contaminated.
The water then moves into tall, round tanks called clarifiers, where the heavy particles settle to the bottom as sludge, and the cleaner water spills over the top and moves on. West Virginia University's team did not stop at that old one-step system. They found that if you move the water through a two-step pH process, you can separate out the metals in a way that makes rare earths much easier to collect. In the first step, they raise the pH to around 4.5. At that level, a lot of iron and aluminum fall out of the water and settle into sludge, but most of the rare earth metals stay dissolved. In the second step, they push the pH higher, up around 8.5. That is where the rare earths finally drop out, along with some other valuable metals like zinc and cobalt. By separating the treatment into two steps, they can pull out a thicker, heavier sludge that holds far more rare earth metals than the usual waste that comes from an old mine. At Richard Mine, the new approach shows up in the way the entire plant is built and arranged.
In the whole watershed upstream of the dam to counteract whatever acidity was still coming in through the
engineers separated the cleanup process into two different paths, so the regular sludge from everyday water treatment moves in one direction, while the rare earth-rich sludge moves in another. That rare earth stream is the one they guard most carefully. The plant pumps this heavier mix into long white fabric tubes called geotextile bags, which lie stretched out in a separate part of the site. These bags act like giant filters. Water slowly drains out through the cloth, leaving behind a thick, heavy mud. Tests show that once this mud dries, it can hold around 1 to 2% rare earth metals by weight. That is a huge jump from the tiny trace levels that were floating in the original water. In plain terms, the plant turns a nasty orange soup into something far more valuable.
So close to WVU is such an asset because of the research that goes on, and Friends of Deckers Creek works closely with Paul's Water Research Institute.
A compact, easy-to-ship pre-concentrate of rare earth metals that can be moved to the next step in the chain. That pre-concentrate is sent to West Virginia University's Rare Earth Extraction Facility in Morgantown, located inside the National Research Center for Coal and Energy. The United States Department of Energy funded this pilot plant so the country could test whether rare earths from waste streams like acid mine drainage could be turned into a steady domestic source. The place looks more like a small industrial plant than a campus building. There are rows of tanks, pumps, steel platforms, and long frames filled with mixer units that run day and night. Firstly, the engineers need to get the metals back into a liquid, but they need to control how that happens. Workers take the dried sludge from Richard Mine and mix it with a mild acid, usually a form of hydrochloric acid or something similar, inside heated tanks. The acid pulls the rare earths and other metals out of the solid and into the liquid, the way warm, soapy water pulls grease off a pan. Once this step is done, they have a strong liquid mix that holds every metal that came out of the sludge.
Fortunately, we don't have a domestic supply of rare earth elements, so we import virtually all of our rare earth elements from the People's Republic of China.
Including the rare earth elements they want and the iron, aluminum, and other metals they do not want. The real sorting happens next through a process called solvent extraction. The name sounds technical, but the basic idea is simple. When you pour oil and water into the same glass, they do not mix. One floats on top of the other. In the pilot plant, one liquid is water-based and holds all the metals. The other is an oil-like liquid that has been tuned to grab rare earth elements while ignoring most of the unwanted metals. The plant sends both liquids through a long line of mixing tanks and settling tanks arranged in a row. In each tank, the workers stir the two liquids together so the rare earths can move into the oil-like liquid. Then they let everything settle until the liquids split into two layers again. They repeat that step over and over. After many stages, most of the rare earth metals have moved into the oil-based stream. Once the rare earths are safely inside that organic liquid, the plant performs one more flip. It washes that liquid with a clean acidic solution that pulls the rare earths back out into water. But now they are far purer than before. After the engineers evaporate the water and complete the final chemical steps, what remains is a powder called rare earth oxide. These powders are what magnet makers, battery makers, and alloy makers buy on the open market. Early pilot systems like this have already produced small batches of mixed rare earth oxide powders with purity levels around 98% by weight. That purity level is high enough to prove that this route can make real commercial material, not just lab samples. When West Virginia University researchers sampled acid mine drainage sludge across coal country, they found that some sites in southern West Virginia held about 666 grams of rare earth elements in every metric ton of dried sludge. Northern West Virginia sites reached around 750 grams per metric ton. In simple terms, that is roughly 1.5 to 1.7 pounds of rare earth metals in every short ton of waste. Those numbers may sound small, but they line up with or even beat some ore bodies other countries mine in open pits. In some cases, the share of heavy rare earths in these sludges is especially high.
Treating it is a complicated process, but one that's being tackled by the DEP and local watershed groups.
Which matters because heavy elements like dysprosium and terbium are the ones the world struggles to supply. To make the numbers even clearer, the team at West Virginia University studied the Omega treatment site near Morgantown, which cleans acid mine drainage from an old coal mine. By using real market prices and actual metal levels, they estimated that the rare earth content of the sludge at that one site could be worth around $1 million over time if every bit were recovered and sold. When you remember there are hundreds of similar treatment systems across the region and that many of them must run for decades just to keep streams safe, it becomes obvious that this is not a small side project. The Richard Mine plant itself is a large, permanent piece of infrastructure. Bringing electricity to the site, building the treatment building, setting the tanks, and installing the clarifiers have cost just over $9 million so far. Most of that money came from West Virginia's special reclamation funds and federal infrastructure programs, because the original mine owner is long gone and the state is responsible for cleanup. The same pattern is beginning to appear at other streams where acid mine drainage has been treated for years. Systems along Three Fork Creek and along tributaries of the Tygart Valley River were first built only to meet water quality standards, but researchers are now studying them as possible future sources of rare earth feedstock as well. And the idea is not limited to Appalachia. The same two-step chemistry developed by West Virginia University is being used at the Berkeley Pit in Butte, Montana, a huge toxic lake that holds tens of billions of gallons of acidic water left over from copper mining. Once you start turning polluted water into the metals that go into electric cars, wind turbines, and modern weapons, you are not just cleaning up old mines, you are stepping into a larger contest over who controls these materials, and the next part of the story moves straight into that clash. Why China is worried about America's new metal source. For years, the United States acted as if rare earth metals would always be easy to get. It closed most of its own rare earth mines and processing plants and chose to buy the finished materials from overseas. From 2020 to 2023, about 70% of all rare earth compounds and metals used inside the United States came from China. China's grip is even stronger when you look at the entire chain from the ground to the final magnet. China produces roughly 70% of global rare earth ore, nearly 90% of the chemicals needed to process that ore, and more than 90% of the finished magnets. Those magnets sit inside electric vehicle motors, wind turbines, fighter jets, radars, submarines, missile guidance units, and the machines that power clean energy systems. When you add everything together, one country holds a controlling position over materials that keep electric cars moving, household electronics running, and advanced weapons operating. Washington realized too late that a huge part of its modern strength rests on metals it does not dig up or refine at home. The one major rare earth mine in California has spent years shipping most of its concentrate overseas, often back to China for processing. This means that if China raises prices, slows exports, or changes its rules, United States companies feel the impact within weeks. Beijing has already shown it is willing to use that advantage. On the 4th of April 2025, after the United States sharply increased tariffs on Chinese goods, China answered with new export controls on 7 key rare earth categories. These included several medium and heavy elements such as samarium, gadolinium, terbium, dysprosium, and lutetium, along with items connected to scandium and yttrium. Export controls mean a company must get a special license to send those metals, or any product containing them, out of China. Officials can delay or deny those licenses whenever they choose. Within months of the new rules, Chinese exports of certain rare earth magnets fell by about 75% because companies could not get their paperwork approved. Automakers in Europe, India, Japan, and the United States all reported supply trouble. Industry groups in Europe warned that engine lines were close to shutting down for lack of magnets, and some factories went into full crisis mode as they watched orders pile up with no parts to fill them. Later in the year, China tightened the limits again. In October 2025, Beijing added even tougher rules that not only cover the metals themselves. The new regulations covered the knowledge behind the metals. Companies now need government approval to export technology related to mining rare earths, processing them, recycling them, or making magnets out of them. Chinese companies and citizens also face new restrictions on helping build rare earth plants in other countries. On top of that, China's industry ministry released interim rules that gave the government far more control over who is allowed to mine or process rare earths inside the country, all under the banner of protecting national security. These moves matter because the numbers behind them are enormous. In the year 2024 alone, China exported about 58,000 metric tons of rare earth magnets, worth nearly $2.9 billion. Germany bought almost 1/5 of that amount, and the United States purchased a very large share as well. When a country with that kind of influence begins using export licenses as a tool in global disputes, every factory that depends on these magnets has to take notice. China says it is acting to protect its own security and answer outside pressure. Chinese officials point to the United States' restrictions on advanced chips and chip-making tools and say they have a right to defend their interests in return. But many Western governments and policy experts believe China is using its rare earth dominance as leverage in a wider competition over trade and technology. In their view, these rules are a reminder that China can make life difficult for anyone who depends on its metals to build electric vehicles, wind turbines, phones, or military equipment. This is where the river story becomes part of a much bigger picture. The acid mine drainage projects in West Virginia, along with tests at places like the Berkeley Pit in Montana, are no longer small science efforts. They are now pieces of a national strategy. West Virginia University and the Department of Energy speak openly about turning acid mine drainage from a long-standing regional problem into a resource that can supply part of the rare earth metals needed for national security. They describe polluted streams and abandoned mine pits as places where the United States can finally build a domestic rare earth source that no foreign government can block. From China's point of view, all of this is a clear sign that its long-running advantage may not last forever. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.